Thank you very much. I'm really happy today to give a brief presentation about some recent work that I've done with my PhD student Mohammad Naseri and Jamie Hayes, who recently graduated from UCL and is now at DeepMind. So this work is going to be published at NDSS next February, and essentially is an investigation of whether or not we can use differential privacy both in the local and in the central differential privacy instantiations to mitigate both robustness and privacy attacks against federated learning. All right, so I probably don't have to spend a lot of time here talking about these attacks, but roughly speaking, we usually reason about privacy in machine learning vis-a-vis three possible attacks. The first one is known as a membership inference attack, where an adversary attempts to infer whether or not a specific data point was included in the training set, so in the data set that was used to train that model. The other attacks are model inversion, where the adversary tries to infer what class representatives look like, or properties of the training data, possibly uncorrelated with the main task. And this is called a property inference attack. So what can we do about this defenses? Well, the way to go is really use differential privacy, and I'm going to get back to this in a couple of minutes. So what about robustness, right? So most robustness attacks in machine learning, and specifically in federated learning, focus on poisoning, where essentially the adversary tries to reduce the accuracy of the model or make it misbehave on specific inputs. And in particular, we will focus on backdoor attacks, where you have targeted model poisoning attacks where you have an adversary, a malicious client or malicious participants that injects a backdoor task into the final model. Okay, so what can we do about this, right? So there's been a couple of really interesting results in this space. So Vitaly Shmadikov and collaborators published a paper a couple of years ago, how to backdoor federated learning, where essentially they show that it's difficult to control the local model that is submitted by some malicious participants. So these attacks are real, and they are not so easy to mitigate. If anything, because the defenses that we typically use against Byzantine adversaries will require access to the data. So access to the training data, or will require inverting the model. And this, obviously, would violate privacy, which is one of the main reasons why you want to use federated learning and not like a fully centralized model in the first place. Then people in this workshop worked on a follow-up paper titled "Can You Really Backdoor Federated Learning?", where they experimented with a number of defenses, namely norm bounding and weak differential privacy, which as we also confirm in our experiments, work okay in most settings, but were not designed with privacy in mind. So we did. Okay, so how do these defenses work? Well, norm bounding essentially requires the server to ensure that the norms of the participants' updates are within a certain threshold. But this obviously means that you have updates that still leak information about the training data. And then they experiment with something called weak differential privacy, which essentially combines norm bounding with some Gaussian noise. And this exploits the composition theorem of differential privacy. But again, this weak differential privacy is a relaxation of differential privacy, and privacy is not really a main objective here. Okay, so our work is motivated by the fact that we didn't seem to have seen any defense deployed in federated learning that would would mitigate both privacy and robustness attacks at the same time. And so our intuition is to actually look at the standard differential privacy, so not weak differential privacy. And as I mentioned, both in the central and local variant of differential privacy, and see if we can use it to defend against both attacks. So what's the intuition behind this? Well, central differential privacy limits the information exposed about the specific participants, right? That's the definition of differential privacy. In local differential privacy, you kind of do the same, you limit information, but about records in a participant's data set. So that's the typical item versus user level differential privacy. So, but in both cases, the impact of poisonous data should be reduced. And this would also allow you to protect against inference attacks, so to provide privacy as per the traditional differential privacy definition. So we did a bunch of experiments, and we used sort of a number of data sets: EMNIST, CFAR10, Reddit comments, sentiment 140. So we use images essentially, and as well as text and other kinds of data sets. So the most obvious sort of backdoor you can imagine is just like a 1 pixel backdoor that you have on a digit. So in the top left image that you see on the slide, but we experiment with actually a number of different settings. And we also actually look at 2 different experimental settings. The first one we call setting 1 is to reproduce exactly the setting in the Can You Really Backdoor Federated Learning paper by Sun et al. And in the second setting, we actually play with the ratio, the fraction of malicious participants. So we increase it, and we try to understand how effective these defenses are when you have an increasing number of attackers. We compute both the main task and the backdoor accuracy, and apply all these defenses. So the norm bounding, weak differential privacy, as well as central differential privacy and local differential privacy. So we do that whenever makes sense on all participants or only on non-attackers. So you can assume that and as will become clear in the setting of local differential privacy, the malicious participants might be able to modify the code that they run, so do not follow the protocol and do not add noise onto their updates. And so we want to see what happens in that case. So here is a snapshot of the results. So you can see, I mean, it's hard to parse, but I'll add the link to the paper. You can, just Google it and find it on archive. But you can see that all these attacks essentially work. They do reduce the accuracy of the backdoor task to some extent. Some more, some less, and obviously some with more or less impact on the accuracy of the main task, so on utility essentially. And obviously there are parameters like the epsilon parameter, which mean different things in central differential privacy and local differential privacy, which is something I don't have time to talk about today, but that obviously is also another important factor. So this was actually, this was in the first setting. So the can you really backdoor Federated Learning paper. So, and then when we play with an increasing number of attackers, we see that some defenses are more robust, let's say, to increasing number of attackers. Some are less. So the accuracy of the backdoor task kind of increases in different ways. So overall, what we find is that differential privacy, both in the local and the central variant, can indeed mitigate backdoor attacks, but obviously they do so with different robustness and utility trade-offs. And our experiments begin to shed light on how these trade-offs unfold across different data sets and different tasks and different system assumptions and system parameters, let's say. The weak differential privacy and norm-bounding defenses also mitigate attack, and they're really good at not reducing utility. However, in the second setting with more attackers, you start seeing a decrease in utility as well. In both settings, we see that local and central differential privacy can be more effective in reducing vector accuracy, but they have more impact on utility. So again, you have to reason about this trade-off, which is not trivial. Remember, I mentioned that in some settings, attackers might refuse to run the defenses, right? They might able to modify the code that they run. This is, a reasonable assumption, and so not apply, for instance, noise on their updates. So do not follow the local differential privacy protocol. And in this case, the attack actually works better than no defenses at all, right? And that's understandable, as you actually make the impact of the poisonous data even more important. Okay, so overall, CDP is a better way to go. It actually mitigates the attack and yields a better utility, but obviously you need to trust the central server somehow, right? So the noise is added at the central server, and that requires trust. So unfortunately, I ran out of time, so I don't have time to cover our experiments with respect to privacy. In particular, we experiment with membership inference and property inference attacks, and we have a whole number of other experiments and insight in our paper. So I encourage you to read it. This is the link. And please do get in touch if you have any questions, either with me or Mohammad and Jamie, of course. Thank you very much for your attention.